now.
Okay, I see the record button. So,
Hey, Hugh,
yes.
what did God say? Can't read it.
Oh, those are Maxwell's equations. I mean, those are the four equations that describe all the properties of electromagnetic radiation. And so thousands of equations boil down to just these four. And if you look at the bottom, and then there was light.
Nice.
I wear this T-shirt because James Clerk Maxwell was not only what I believe to be the greatest physicist who ever lived, he was literally on the verge of discovering general relativity and quantum mechanics before he passed away in the late 19th century from a stomach condition. He was only like 46 years of age when he passed. But yeah, when they looked at his notes, if they had read his notes earlier, they would have had general relativity and quantum mechanics decades earlier.
Wow.
Also, James Clerk Maxwell was one of the top leaders in the Presbyterian Church, very committed Christian, very powerful evangelist, and they said he was the best theologian in the Presbyterian Church, even though he was a theoretical physicist. So he's kind of my hero, which is why I wear this T-shirt.
Got it.
And I get lots of questions. It gives me a lot of opportunities to share my faith. And I actually run into people who know what the equations actually mean. So that's always fun.
Wow.
Yeah, if you're a physics engineering student, you study these equations literally for years.
Yeah, that's why I'd be afraid to wear that shirt.
Okay, you want me to get started, Jane?
Yes, please.
Okay. Brief introduction. I'm an astrophysicist. I also pastor in a church that's in between the Jet Propulsion Laboratory and Caltech. It's an unusual church. We have scientists, engineers, atheists from the Skeptic Society, which is just a few miles away. And we're also close to Fuller Seminary. So you can imagine the kind of debates and discussions we have at that church. But that's what I especially enjoy about the church. In fact, I run a class every Sunday called Paradoxes, which is a class for skeptics where we encourage debate on science faith issues. And I'm also the president and founder of Reasons to Believe. And that's an organization where we integrate God's two books, the book of nature with the book of scripture. And basically, we're involved in taking the latest discoveries in the book of nature and using those to bring people to the book of scripture and into a relationship with Jesus Christ. And if any of you are out there interested in wanting to pursue a graduate education in research science, we actually have a scholar community of research scientists from around the world. We're also now having an associate program where we invite graduate students and postdocs to be equipped to share their faith with their peers. And of course, we have a website, reasons.org, and you can go there and you'll literally find more than 10,000 articles on science faith issues, as well as a lot of videos and video recordings of debates we've had with some of the leading atheists that are out there. And with that, I'm going to share my screen because I prepared a little talk for you on climate change. And I've just finished writing a book on climate change. It's called Weathering Climate Change. Let me actually run up my, here we go. Okay, you should all be seeing my first slide now. And this slide basically gives you an opportunity to ask questions. We're going to have a Q&A time after I'm done with my talk. But if you don't get to ask your question, I do take questions on both my Facebook and a Twitter page. And I use those pages to alert you to the latest scientific evidences for the Christian faith. And Reasons to Believe has a 24/7 YouTube channel. Encourage you to subscribe. If you do, you'll be notified of all the latest videos that we're posting there. At the bottom is our website, reasons.org, where you can literally spend days and weeks going through our articles and DVDs. And much of what I'll be speaking about tonight, you'll find in these two books, Improbable Planet, where I talk about the fine-tuning of our planet Earth that makes possible the existence of billions of humans on our planet. And this is my latest book, Weathering Climate Change. And you can get a free chapter of either book or both books by going to reasons.org/Ross. In fact, anyone can get free chapters of most of my books by going to that reasons.org/Ross. So, weathering climate change, and three questions I'm going to be addressing in this talk is how do we get such an extremely stable climate for the past 9,500 years? Is the current climate change something that's real? Is our planet really getting warmer than it's been? And if so, are economic sacrifices needed to rein in global warming and sustain extreme climate stability? So those are the three questions. I'm going to basically go through this material quite rapidly at a lay level. And if you want the details and you want the documentation, I encourage you to pick up the book, Weathering Climate Change. So the first point I want to make is that for billions of people to live on our planet, we must be living in, there's something wrong with this, it's not advancing. Let me see if I can get this to advance. Here we go. Yeah, for billions of people to live on our planet, we must be living during an ice age cycle. And we've been in an ice age cycle for the past 2.58 million years. And right now we're in what's called an interglacial. And so the ice age cycle goes from a lot of ice on planet Earth to a little bit of ice. And North America is the continent that's most heavily impacted by the ice age cycle. And so when the ice is at a minimum, about 10% of North America is covered with thick ice. But most of that thick ice is in Greenland and Ellesmere Island in the northern Canada. But during the height of the last ice age, this is how much of North America was covered by thousands of feet of ice. 55% of the North American continent was covered with ice. In fact, during the last ice age, thousands of feet of ice penetrated all the way into southern California. So for example, the big deep valleys in Yosemite, they were carved out by the retreat of ice from the last ice age. And during the last ice age, during the winter time, San Diego, the port of San Diego, was totally frozen in. It was ice-free in the summer, but frozen in during the winter time. But this is what our continent looks like today. And then the ice age cycle currently looks like this, where it's about 100,000 year periodicity, and you get about 90,000 years of 23% of our planet being covered with thick ice. And then you get a warm interglacial where 10% of our planet is covered with thick ice. So this is how it's been cycling for the past 800,000 years. Now, I'm going to just very briefly tell you why we have to be living in an ice age cycle for billions of people to be able to exist at one time on planet Earth. In my book, Weathering Climate Change, I list over 15 different specific benefits we gain from living during an ice age cycle. I'm just going to hit a couple of highlights for you right now. And again, I'm having trouble advancing these slides. Let's see, come on. What's happening here? Here we go. Melting glaciers left over from the last ice age water the great plains, the great agricultural plains of our planet. And so we still have lots of ice left over from the last ice age, Antarctica, Greenland, the polar ice cap. We have a huge amount of ice still in the Rockies, especially the Canadian Rockies. And then we got an enormous amount of ice in the Himalayas and the Tibetan Plateau. This next slide, again, here we go. This slide shows you the extent of thousands of feet of ice that existed on our planet just some 25,000 years ago. And you can see in the Himalayas, for example, that yellow region kind of shows you where the ice is today. But for example, the 20 largest rivers in terms of water flow coming out of Eurasia flow out of the ice cap that overlays the Himalayas and the Tibetan Plateau. And it's because of that melting ice left over from the last ice age that India and China and Southeast Asia are able to grow sufficient food to feed nearly 4 million people. And the same thing's true in North America. Leftover ice in the Cordillera Range of British Columbia and Washington, that melting ice is feeding the great rivers, which water our great agricultural plains. And likewise, we see that in Europe. You got the Alps covered in ice, you got the Caucasus, and again, you got great rivers flowing out of there that water the agricultural plains of Europe. And so we also have this phenomena that when you come out of an ice age, you've got thousands of feet of thick ice over Siberia, almost all of Europe and North America, over parts of Australia, and it melts rapidly. You literally get thousands of feet of thick ice melting in just 1,000 years. And that rapid melt of ice, when the ice is no longer weighing down on the continents rebound. They basically bounce back up, being liberated from the weight of overlying ice. And that rebound, that gravitational rebound, ignites volcanoes all over the world. So you get this sudden burst of hundreds of volcanoes all over the world. And that has the benefit of dumping very rich volcanic ash on the great agricultural plains. And likewise, as that ice retreats, for example, from the Tibetan Plateau, it drops nutrient-rich dust over the great agricultural plains of India and China and Southeast Asia. And so with each ice age cycle, you get a huge fertilization event, and then you got the melting water left over from the last ice age. And a benefit that's seldom noticed, but something that I think we all appreciate when we go on vacations, is that we are living in an interglacial that follows the most severe ice age in the entire ice age cycle. And it retreated more rapidly than any other ice age that exists in the ice age cycle. And consequently, it carved out these gorgeous scenic canyons, literally all over the world, created fjords and great harbors. One reason why trade is able to be as efficient as it is, the retreat of the last ice age carved out these magnificent harbors all over the world. And so you have these magnificent safe harbors, which facilitate sea trade over the oceans. And I think most of you, having been here in California, recognize this slide. This is Yosemite Valley, and it was literally carved out from the retreating ice of the last ice age. And there's actually another valley that's just as spectacular as this in Yosemite Valley. It's at Hetch Hetchy Reservoir. For some reason, our politicians decided to dam it up and fill it up with water, and there's been quite a stir. Let's take that dam down and actually open up another really scenic valley for peoples of the world to enjoy. And we see that this is happening all over the world. Believe it or not, this particular canyon is only visited by an average of about one person every 2 years. I had an opportunity to go there. It's actually an 8-hour, very arduous bushwhack to get into this canyon. But when you're there, you're surrounded by 25 giant waterfalls coming over cliffs that are a sheer 2,000-foot drop. As you're walking in the canyon floor, there's wildflowers everywhere. There's blueberries, raspberries, wild strawberries. I mean, it's just almost like the Garden of Eden, an incredible experience. But only at this particular time in the history of the earth, the past 10,000 years, has this kind of scenery even existed. And it's like God knew that we need places of natural retreat that we could go to recover from the high stress of living in a high-tech, high-population world. So those are just a few of the benefits. You'll find a whole lot more in weathering climate change. And I just want to share with you that stars are kind of like human beings. They're unstable when they're young, they're unstable when they're old, they're maximally stable when they're middle-aged. For humans, the stability period lasts for a long fraction of our lifespan. That's not the case with stars. And of all the stars that exist, stars that are the same mass of the sun have the least flaring activity. But this is the flaring activity curve for our star, the sun. And the y-axis is logarithmic. And what that tells us is that when the sun was young, its flaring activity was about 100,000 to 1,000,000 times greater than it is today. And right now you can see from that dotted line, we're at that minimum, where the flaring activity is minimum. Basically making the point, if you want advanced life on planet Earth, you can only have it when our planet is 4.57 billion years old. And that's exactly the age of our star and our sun right now. We're at that very minimal point. In the future, the sun will begin to flare at a level that'll rule out the possibility of advanced life. And what we've discovered, we astronomers have discovered by measuring neutrinos coming out of the sun, is that the date for this flaring minimum occurs when the sun is exactly halfway through its burning cycle, which occurs when it's 4.57 billion years old. But that as it goes into this flaring minimum period, it also enters into a period of extreme luminosity stability. But we now know this period of extreme luminosity stability for the sun lasts a little bit less than 100,000 years. You say, where are we right now? We're right at the halfway point of that 90,000 year period. Now, this poses a problem in terms of trying to have an ice age cycle on the planet, because stars like the sun get brighter and brighter as they get older and older. So this shows you the luminosity of the sun throughout the history of life on planet Earth, and reveals that the sun today is brighter than it's ever been in the history of life on planet Earth. And for 90% of Earth's history, our planet has had no ice at all. You know, you would expect that our planet would be totally ice-free today, given how very bright the sun is. And there's a number of reasons why, in spite of the sun being exceptionally bright, we have ice on planet Earth, an ice age cycle, and therefore the possibility of being able to grow sufficient food to feed billions of human beings, plus all their domesticated animals. And what I'm going to just share with you briefly is a few of the things we know must be in place in order to have an ice age cycle when the sun is so exceptionally bright. And of course, we can't go back any earlier. If you go back any earlier, the flaring activity would rule out the possible existence of advanced life on planet Earth. You say, how come life has been here for 3.8 billion years? Well, for most of that history, more than 3 billion years worth, the only life that existed on our planet was microbes. And microbes can handle a lot of nasty flares from the sun, but animals cannot. And particularly human beings are very intolerant to that kind of radiation. But what we now know is that there were 3 giant asteroids that struck the Earth at just the right location, at just the right time, to enable us to be in an ice age cycle where we have a warm interglacial with extreme climate stability. And so this is the first of these giant asteroids. And by the way, asteroids of this size are rare. You typically get one about every 50 million years. We've had 3 in the past 2.6 million years. So we're living during an exceptional period of bombardment. And that's particularly unusual because in the solar system, the rate of bombardment goes down with respect to time. And so I believe this is truly supernatural. And also because these asteroids were just the right size, of just the right composition, hitting at just the right time and location to bring about this extreme period of climate stability. The little red dot there indicates the collision point of the Eltanin impactor. And it struck in a part of the Pacific Ocean that was 17,000 feet deep. And and if you go to the bottom there, what happened? And this is literally by chance. There happened to be a ship that was exploring the bottom surface. And they noticed some unusual structures. They didn't see a crater. Being this deep, even a giant asteroid wouldn't form a crater at the bottom. But as they examined samples from the bottom floor, where they saw these unusual features, they saw the isotope signatures that told them there was a giant asteroid that struck here. They were able to determine the date. It happened 2.51 billion years ago, plus or minus 0.07. They calculated that the impactor had to be a minimum of 4 kilometers in diameter and could have been as large as 4 kilometers in diameter. If it had struck on land, the crater would have been at least 35 kilometers across. And as they explored the bottom of the ocean, debris from the asteroid collision was spread over 500 square kilometers. And papers have been published showing that this asteroid striking this deep part of the ocean would have hit the bottom, would have caused the rocks and chemicals of the bottom to mix with the ocean water and be blasted up into the atmosphere as a thick aerosol. An aerosol cloud so thick it would have blocked out the light of the sun for several years and bringing about extremely cold conditions over the entire planet. So even though the sun at this point was brighter than it's ever been, thanks to this collision event, there was a global cooling that for the first time allowed the Arctic ice cap to form. And so there was an ice cap over Antarctica. This collision event made that ice cap much bigger and much thicker, but it actually caused ice to form over Greenland and particularly the Arctic Ocean. And we've seen geological evidence of this. By the way, when it hit in the ocean, it set up tidal waves running through the Pacific, the Indian, and the Atlantic Ocean, where the tidal waves were 1,000 feet high. And that they've actually discovered a wash up of mud all through the Adriatic Sea and the Mediterranean, showing that mud was piled up 1,000 feet above sea level. So this went through, and they found evidence of these tidal waves along the shorelines of North America, South America, Asia, and even Europe and Africa as well. And so without this collision event, there would be no ice age cycle today. And then we have a second event. This happened 800,000 years ago. And this may have been a giant comet because we actually see two crater sites, one on top of the Spratly Islands in the South China Sea. That's that big blue and red circle you see there. But if you look off to the left in Laos, you can see an oval blue circle, and that represents a secondary collision site. And so astronomers believe there is a giant comet that went through the Earth's atmosphere. And comets being 85% frozen water, you've got a high likelihood that it's going to split up as it goes through the atmosphere. And often you get 3 or 4, even 5 craters. So far, 2 have been discovered. And it's now known, for example, that the Spratly Islands before this collision event was much larger. And so what happened is this comet hit in that part of the South China Sea. The large Spratly Island there basically got demolished, and all that's left are a few tiny specks of islands that are surrounding that crater site. But what this did is it sent up a vast cloud of debris throughout the solar system. And our planet goes through that debris cloud about once every 100,000 years. And what this did is it changed the periodicity of the ice age cycle from about 41,000 years to about 100,000 years. When the ice age cycle was initiated 2.58 million years ago by the L-Tannin impactor, the cycle was driven by the variation of the tilt of Earth's rotation axis. Earth's rotation axis, thanks to the gravity exerted on it by the moon and the sun, it tilts back and forth by about 2 degrees over a cycle of 41,000 years. And when it tilts towards 24.5 degrees, our planet warms up. When it goes back to 22.1 degrees, it cools down. And right now, just if you're wondering, we're in the cooling phase of that cycle. But what happened with the impactor in the Spratly Islands in Laos is that it changed the ice age cycle from a 41,000 year period to a 100,000 year period, which meant that the warm interglacials, instead of lasting 2,000 years, could now last 10,000 years. And that gives enough time, for example, for humans in an interglacial to launch and sustain global civilization. And this is what the previous three ice age cycles look like in terms of temperature variation. And so what's being measured here is the global mean temperature. And what you see here is that when you come up out of an ice age, the temperature rises very quickly to a maximum. It hits that maximum and almost as quickly drops back down into a long cooling phase, and then it jumps back up again, and then you have another long cooling phase. It explains why we have about a 90,000 years of an ice age interleaved by 10,000 years, and typically much briefer than that. Even with a 100,000 year periodicity, the norm is for the warm interglacials to last only a couple of thousand years. The exception is the one that we're in now. But this next slide basically shows you in detail what the global mean temperature looks like throughout the ice age. And this would include both an ice age and the warm interglacials, is that the global mean temperature jumps up and down by about 18, 19 degrees Fahrenheit over time scales of just a few centuries. This explains, for example, why humans living during the last ice age were not able to launch and sustain global civilization. If you go on our website, you'll see articles I've written about new discoveries showing, for example, that during the last ice age, as far back as 34,000 years ago, we have evidence that humans were planting a variety of grains, reaping those grains, and then they would be roasting them and grinding them and turning the ground flour into bakery products. Really sophisticated agricultural industry was going on, but it was all on a very small scale. People were planting maybe 1 or 2 acres, and they couldn't afford to plant just one grain. Because of how unstable the climate was, they would typically plant a dozen different grains, knowing that most of them would fail, but the few that would not fail, they would turn into bakery products and to feed their families. And I believe this is also true of a lot of other industries. I think we now know, for example, that humans living during the last ice age were actually involved in metallurgy. We know in particular that they were harvesting these fragments of stainless steel asteroids and cold forging them into sophisticated stainless steel tools. And they may have been doing hot forging as well, but it was all on a very small scale because there simply wasn't the climate stability to be able to scale up any kind of industry. Now, all this changed starting about 9,500 years ago. Here's a temperature graph showing the global mean temperature over the past 17,000 years. And the pink part of the graph basically shows you kind of the norm for climate variability throughout the entire 2.58 million year ice age cycle. The exception, and the one and only exception during the entire ice age cycle, is what you see with that blue line for the past 9,500 years, where the climate went extremely stable. And so this is the remarkable thing about our past 9,500 years. We're in an ice age cycle, and we're in a warm interglacial, but it's a warm interglacial where the climate has been extremely stable. Now, this is the latest temperature graph that's been produced. It supersedes what you see in your textbooks. We now know, for example, the climate of the past 9,500 years is 4 times more stable than what scientists previously thought. the global mean temperature has not changed by more than plus or minus 0.65 degrees over the past 9,500 years. And it's that extreme climate stability that enabled humans, as we're coming out of the last ice age, to launch and sustain global civilization. The beginning of that blue line coincides with what we call the Neolithic Revolution, when people began to build cities for the first time and roads where they began to trade, where they began to scale up their agriculture and specialize in different industries. We actually have towns where they don't produce any food at all. They produce tools and pottery and basically trade the tools and pottery for the food that other groups of people were specializing in. Now, I want you to notice that dotted line where it basically shows us, starting 17,000 years ago, rapidly the planet is warming up. And it begins to go up towards the typical maximum of 2 degrees centigrade above where we are now. But what happened was there was a cooling event. It's called the Younger Dryas cooling event, where instead of the temperature rising up to its normal maximum, it suddenly drops. And it drops by about 10 degrees centigrade and stays at that very cold phase for 1,200 years. And then it begins to warm up again, but it doesn't approach the normal maximum. This is good news because when you get to that normal maximum, it melts the polar ice cap. And when you melt the polar ice cap, instead of the Arctic Ocean reflecting sunlight with 60% efficiency, with the ice gone, it reflects it with only 6% efficiency. So what happens to all that extra solar heat? It makes water vapor, and that water vapor falls as snow over Siberia and Canada and Greenland and Europe and brings on the ice age. That's kind of the irony. Global warming always brings on global cooling when you're in an ice age. But thanks to this cooling event, we did not go up to that normal maximum. The polar ice caps survived, and Canada and Siberia, even though they're plenty cold enough to build up snow, because they get so little snowfall, literally less than 10 inches of precipitation equivalent a year, the ice cannot accumulate. Canada and Siberia are actually technically deserts. It's cold enough that you don't get much water vapor evaporation, so it doesn't look like the deserts of Sahara, for example, but they literally get very little rainfall. And that's thanks to that, we don't get a buildup of ice over those regions. What's been discovered just before I brought the book out, I actually delayed bringing out Weathering Climate Change in order to include the latest science that for the first time explains the Younger Dryas cooling event. And kind of like the L-Tannin impactor, it was a serendipitous discovery. What happened was that a NASA science aircraft was flying over northern Greenland, and they happened to have their ice penetrating radar turned on. And they noticed that they saw an unusual feature under 3,000 feet of ice in northern Greenland. And this is the location of that feature. It's at the edge of the Hiawatha ice field in northwest Greenland. And here is a blow up of exactly where they discovered this. The crater is more than 30 kilometers in diameter. And you can see it's right there at the edge of the Hiawatha ice field. And so when the aircraft returned to its base, they alerted a team of geophysicists. They went to the site right at the edge of the Hiawatha ice field, and they were able to measure the meltwater coming out from under the ice field, and it had all the isotope signatures of a giant stainless steel asteroid striking that particular region. And they were able to date it 12,800 years ago, exactly coincided with the beginning of the Younger Dryas cooling event. And this had a dramatic effect on the climate of the Earth. At that time, ice was retreating from North America, but the retreat of ice created a gigantic glacial melt lake. This is Lake Agassiz, as it existed about 13,000 years ago. a giant lake filled with the meltwater from retreating glaciers, and it drained into the Gulf of Mexico. But when this Hiawatha uh, asteroid struck in northwest Greenland, it threw up huge rocks and chunks of ice that bombarded all of Canada and the northern US. And that bombardment resulted in changing the flow of meltwater from Lake Agassiz. It basically blocked the flow into the Gulf of Mexico and opened up two new flow patterns, one through the Great Lakes and out through the St. Lawrence River, and one through Great Slave and Great Bear Lake out into the Beaufort Sea in the Arctic. And at that time, there was a strong ocean current that flowed through the Canadian Arctic archipelago and basically caused the cold meltwater flowing out through the Mackenzie River into the Beaufort Sea. It caused it to flow eastward and flowed between Baffin Island and Greenland and out into the North Atlantic, where it melt the equally big flow of a cold meltwater from Lake Agassiz through the St. Lawrence via Newfoundland and out into the North Atlantic. The net impact of that is it turned around the Gulf Stream that flows through the Atlantic. You're probably aware from your elementary school education that it's the Gulf Stream flowing through the Atlantic that keeps Europe warm enough that snow and ice do not accumulate. But when that was turned back, thanks to this flow, this huge flow of cold glacial meltwater, that caused a cooling event over North America, over Europe, over Siberia, and actually led to a global effect. They now know it literally cooled the entire planet, including the southern hemisphere. And the cooling event lasted 1,200 years. And that prevented the global mean temperature from rising to its typical maximum and melting the polar ice cap. And likewise, it was responsible for bringing about a period of extreme climate stability. And basically what happened, thanks to the Hiawatha impactor, it briefly brought about a period of extreme climate stability, and humans immediately took advantage of that and launched civilization. But the launch of that civilization brought about warming effects, human activity, cutting down trees, especially domesticating cows and domesticating wheat and rice. As I explained in Weathering Climate Change, those the development and expansion of human civilization and technology brought about a worldwide warming effect. However, where you see the beginning of that blue line is also when we see the shape of Earth's orbit around the sun changing from being more elliptical to less elliptical. And so starting 9,500 years ago, the planet began to cool as a result of the change in the shape of Earth's orbit. That was also the time when the tilt of Earth's orbit, or the tilt of Earth's rotation axis, was at 24.5 degrees, which means we're at the maximum warming effect. And then it began to move. Right now it's at 23.5, but we are moving towards 22.1. So if it wasn't for human activity, you wouldn't have that steady blue line. Instead, the planet would be the global mean temperature would be rapidly cooling down and bring us quickly into an ice age. But thanks to this brief period of climate stability, human activity began to warm the planet at almost exactly the same rate that the natural cycles were cooling the planet. And if you look carefully at that blue line, you can see that throughout the past 9,500 years, you're getting a very, very subtle global mean temperature decline. In other words, for 9,500 years, the natural cooling cycles were slightly superseding the warming effects from the advance of human civilization, population, and industry. In fact, if you were to measure the global mean temperature in 1950 was 1 degree centigrade colder than it was 8,700 years ago. That's when the temperature hit a peak. But what has happened in the last 70 years is it's warmed up by 1 degree. Again, if you look carefully at this curve, you'll see that it's jumped up a full degree in the last 70 years. So right now, the planet is just as warm as it was 8,700 years ago, which is not a problem. However, if we continue on this trend of warming the planet by a degree every 70 years, we're looking at only a couple of centuries before we melt the polar ice cap. And with that, we're going to catastrophically bring ourselves into the next ice age. And what I put in Weathering Climate Change was an analysis of the past 9,500 years based on 74 independent temperature proxies. For the first time, we've got really accurate and reliable measurements of the global mean temperature over the past 9,500 years. But it's basically the exponential acceleration of a human civilization and technology over the past 70 years that's caused human activity to supersede the natural cooling cycles. Now, you'll find a lot more about this in Weathering Climate Change. I basically point out that this period of extreme climate stability simultaneously overlaps several other extremely exceptional events in the past 10,000 years. I'm briefly just going to share with you one, namely that we're living these past 10,000 years in a unique supernova window. Uh, this photo here basically shows you a supernova in the galaxy NGC 4526. It exploded in 1994. And what happens is for about a 5-month period, a single star will be so bright, it will shine with the equivalent light of another 100 billion stars, almost becoming as bright as the entire galaxy in which it has exploded. And so this is what NGC 4526 looked like before the supernova eruption. Then you can see that it briefly brightens and then it disappears. And these supernova not only are very bright, they blast deadly radiation throughout its galaxy. But this particular table shows you the norm for our Milky Way galaxy, where we're getting like 20 to 30 nearby supernova eruptions within a 50,000 year period. In fact, a paper here got published making the point that we now know that 23 supernova exploded less than 1,000 light years from the Earth during the past couple of 100,000 years. And you'll get the citation, Weathering Climate Change. This is what was going on during the last ice age. Now, these are close enough that it actually affects human health. It doesn't kill everybody, but it does affect human health, and it especially affects agricultural productivity. So you simply can't grow much food when you got supernova that are this close. But this is the norm. The exception is the past 10,000 years. During the past 10,000 years, we not only don't have supernova exploding within 2, 3, or 4, or 500 light years of us, we don't have any exploding even within 5,000 light years of us. The closest one was 5,080 light years. That's so distant, it has zero effect on our crop productivity and has zero effect on human health. But notice this period of extreme lack of nearby supernova exactly coincides with the period of extreme climate stability. And there are another 10 or 12 exceptional windows that I talk about in Weathering Climate Change. And you say, why? Well, I think the reason why is Revelation 7:9, where John has this vision and he sees the hosts of redeemed humans in heaven. It says, before me was a great multitude that no one could count, from every tribe, nation, people, and language. And at that time, the Greeks had a numbering system that would go up into the billions. So this is basically a statement making the point that God's intent all along was that billions of human beings would be able to live on the planet at one time and have the technology where the good news of salvation through Jesus Christ could be communicated to those billions of people all over the world, where billions can hear the gospel message and respond within a short period of time. Now, I notice I've gone about 40 minutes. I had some slides here prepared on how we can continue to stabilize the planet. I'm just going to cut through this. There's 2 whole chapters on this and weathering climate change. That was one of my main motivations in writing the book, was to demonstrate global warming is real. We are at risk of returning to extreme climate instability with its catastrophic consequences, but there are things we can do to manage our planet where we boost the world economy rather than cripple the world economy. Because that's the problem I have with books written by Al Gore and others. They're basically saying global warming is real, we're in danger of losing our climate stability, and we need to undergo draconian economic sacrifices to continue to stabilize the climate. Like, for example, forbidding people to drive cars or forbidding them from going on airplanes, shutting down all the factories, and not allowing people to burn fossil fuels. And I'm basically making the point in weathering climate change, not only are those draconian measures not necessary, we can actually sustain climate stability while we dramatically boost the world economy, and especially for the poor people of the world. So, and one of the things I talk about is how we can shrink the Sahara Desert down to 1/10 of its present size. That can be done in just 1 or 2 generations. And likewise, we can better manage our jungles and rainforests in such a way that they produce a higher income than if we simply cut down the forests and actually withdraw more greenhouse gases out of the atmosphere. And one thing I didn't get to put in weathering climate change, or just a hint of it in there, is that we actually have the potential to replace all of our power generating stations from, say, burning coal or natural gas, or using uranium fission. We can replace that with thorium fission. And thorium fission has the potential of producing immense amount of energy for a fraction of the cost of nuclear fission and a fraction of the cost of coal and oil production. And it's safe. Unlike uranium fission, you can handle the thorium without wearing any kind of safety gear. It's impossible for the thorium reactor to melt. It's impossible to use a thorium reactor to make weapons. And the US has enough thorium to produce 100% of its total power needs for over 1,000 years. And the US doesn't even have the largest reserve of thorium. I gave a whole talk on this to our scholar community, and it's up on our reasons.org YouTube channel. Again, if you want more details, check out Improbable Planet or Weathering Climate Change. You can get a free chapter at reasons.org. And with that, let me bring us back where we can take some questions. And I'll take questions on any topic. It doesn't have necessarily be what we've been talking about in my message tonight. So Jane, I'll let you manage the Q&A time for me.
Yeah, so if you want to ask a question, you could either put it in the chat box or you could just unmute yourself.
I'll ask a quick question. Hugh, thanks for your talk and appreciate this. Joe Miller. I can turn on my video for a few minutes here, I guess. Sorry. Yeah, you know, I don't know how to phrase this right, but if what you're saying is true and you know, the data is I mean, when you say it, okay, it's obvious, oh, it's clear, there's all this data and it shows what these cycles are. Why, I mean, are there scientific reasons why this is rejected? I understand there's political reasons why some people would rather focus on man-made and the Al Gore stuff, as you mentioned. But if is it really as clear, this data is clear as you say it is scientifically, or are there different ways of interpreting some of this that would lead to different conclusions? I guess I'm just wondering if it's so clear within your book, why aren't there more scientists? And to my knowledge, and I don't study this closely, maybe there are, that talking about this. So hopefully that makes sense.
Well, it wasn't that clear 4 years ago. It is clear now.
Mm.
And so I have a chapter in the book pointing out that there is now a scientific consensus that this data is real, it's highly reliable, it's indisputable. There's still a debate going on though. When I talk to people who used to deny global warming, they're no longer denying global warming. The denial is over what's responsible for the global warming. So you still have people saying, well, it's not human activity, it's natural causes, which is why I put so much time in my book and pointing out it's a combination of natural causes and human activity. But we have overwhelming scientific evidence that the natural causes are working to dramatically cool our planet. There's nothing natural that's warming our planet, nothing significant that's warming our planet. So the warming has to be from human activity. But I think the main reason why we have so much scientific and political pushback is basically you've got politicians and some scientists saying the only way we can restore order is by making huge economic sacrifices. And what they're overlooking is a biblical principle. The Bible tells us that we human beings are sinful. We're fundamentally selfish. And I mean, you can take a survey throughout your Ratio Christi groups. How many of your members are willing to live on 1/3 of their present income? How many of them are willing to let go of all their high-tech toys? I mean, I took a survey of all my son's friends, and they said we would rather see the end of human civilization and the extinction of the human species than to do without all of these, benefits of modern civilization and technology. Which is why I think if we're going to motivate people to address climate change, restore climate stability, we have to give them an economic motivation. Telling them to make an economic sacrifice is, I don't think it's possible to sell it. And I think that's one reason why there's so much delay. You've got people digging in their heels, politicians and scientists included, saying, we're not going to do this because it's just too painful. We need to provide people with a painless solution. And more than that, not just a painless solution, but say, here's a way you can put a lot more money in your pocket. Here's a way you can really increase the wealth of your nation. Here's a way you can really benefit the poor in your nation. And so my whole point is, if you give people a win-win solution, they will do it. And they'll do it quickly. I mean, if you go to a businessman and say, here's a project whereby you're going to get a 20% return on your investment every year, you're not going to have to tell them, you really need to get busy and do this now. If they see a 20% return on their investment per year, they're going to operate on it tomorrow. They're going to say, hey, let's jump on this. Matter of fact, economists will tell you, even if you give people just a 5% economic incentive, they'll do it, and they'll do it quickly. But if you give them 20, 30, 40, or 50%, they'll jump on it. And frankly, I think that's the only way we're going to be able to stabilize the climate in the time window we got left. We don't have a lot of time to fix this. And therefore, I think we have to give people around the world a strong economic incentive. And what I really love about the proposals I put in Weathering Climate Change, they're not only giving peoples of the world an economic benefit, it's a health benefit. We'll all live much healthier lives if, for example, we stop depending on beef for meat and instead depend on ostrich meat. It's way healthier, and you get 50 times less greenhouse gas emissions if you basically encourage people. And by the way, it's tastier. It's got a higher content of nutrients in it and almost no saturated fat or cholesterol. I mean, and you could actually, if you scale it up, the meat will be less than half the price of turkey, which currently is the cheapest meat in the market today. So it's just an example where everybody wins. Now, I must make one caveat. There's one downside to depending on ostriches for your meat. They need social contact with humans. They're highly social animals. They're not like cows where you can just ignore them. They need social contact with one another, and they especially need contact with human beings. If you treat them like pets, they're going to produce marvelously for you. If you treat them like cows, you're going to go broke.
Doc, are you suggesting end of fossil fuels and going to solar and wind power?
I'm not a big fan of wind power because you have to burn a lot of fossil fuels to maintain the wind. I mean, those wind vanes are not easy to manufacture. And have you ever been to a wind farm?
Yeah.
You notice they're all tuned to a particular wind velocity. And so if you're wondering why only 20% of the windmills are actually spinning, that's because, well, they're tuned to a particular wind velocity and the other ones are not. And so it's a very inefficient way to generate power. It's expensive. And if you actually look at the total carbon footprint for wind, it's something we should not pursue. And incidentally, it kills millions of birds. So it's not an eco-friendly energy generation. And so what I'm arguing in the book is that we pursue sources of energy that are cheaper than fossil fuels and actually benefit the ecosystem rather than harm the ecosystem. And actually, we'd be wise to reserve our fossil fuels for developing plastics and chemicals rather than just simply burning them. On the other hand, it's thanks to fracking that the United States has reduced its carbon footprint. And so we're far better off getting fossil fuels locally than importing it from overseas. And so, thanks to fracking, the US has the potential of being completely independent for its fossil fuel needs. That explains why, over the last 10 years, the carbon footprint of the US has gone down, whereas for nations like China and India, it's gone way up. It's because we found ways to get all the fuel locally that we need. And and you actually have a lower carbon footprint with natural gas, for example, than you do with coal. And of course, you got health consequences with coal.
Can we talk a little bit about thorium? It's weird, I haven't heard of that before, but I assume you must know a fair bit about it.
Yes. What's the question?
Oh, like how does that work? Why, if it seems to be all positive benefits from there. So my curiosity is why hasn't everyone started doing this?
Well, the US had a couple of thorium reactors that date back to the 1960s. They were basically small scale projects. They've been shut down. And the reason why we didn't pursue thorium power generation back in the 1960s, you couldn't make weapons out of it. And so they said, we're going to go with the uranium because we get weapons as a byproduct. Well, today, people are now getting interested in thorium for the very reason you can't use it to make weapons, which means that we could actually give a thorium reactor to a third world country and not worry about them using that to make weapons that they use against us. You can make weapons from thorium nuclear reactors, but if you try, you'll die. And so the people, you won't be able to deliver the weapon before you get killed by it. So no one in his right mind is going to try to develop a weapon from a thorium nuclear reactor. And one of the big benefits is it's impossible to have a meltdown, and it delivers way more energy per pound of thorium than you get per pound of uranium. And we have 3 times as much thorium in the crust of the earth as we have uranium. It really is win-win all the way around. And nations of the world are beginning to recognize the potential. The United States, Canada, India, and Israel are now developing thorium nuclear reactors. What I'm arguing in my book is we need to speed up the scaling of thorium nuclear reaction. I mean, that's really the only engineering difficulty, how to take the existing thorium nuclear reactors and make them hundreds of times bigger and do it in a way that's economically feasible. But the potential is we could produce all the energy we want for less money or for less than what we get from water power. Water power today is the cheapest source of electricity. Thorium is a potential to deliver energy for less than half of the cost of being close to, say, the Niagara Falls.
Hello, my name is Noes. First, I want to say thank you for doing all your work to about climate change. In the past few years, it's hard for me to. It's been frustrating for me to. There are some people denied climate change, even though others like consumed by their own sins. Like I don't want to see Jesus Christ come here on earth and tell him why the earth so chaotic and you know have their own climate change stuff. Yeah. So yeah, I want to say thank you for helping the young generation like us, just relax a little before us trying to fight for climate change until it's too late.
I think the major source of controversy and pushback is the idea, well, we need the government to step in and pass laws. I mean, here in California, our state legislature is basically going to ban gasoline engines in cars by 2035. And, that they don't realize right now, California gets most of its electricity from burning fossil fuels. And so, I drive a Honda Fit. It's way more efficient in terms of its carbon footprint than an electric car, because our electric cars have to get their electricity from burning natural gas, and is nowhere near as efficient as my gasoline engine. I'm getting about 40% efficiency. The best you get with an electric car is 25%. It's actually a bigger carbon footprint. Of course, what our state legislature wants to do is say, what we're going to do is we're going to blanket the Mojave Desert with solar power generators. Well, right now, solar power is not cost effective with fossil fuels. It could be, but right now it's not. And therefore, you're having to spend a lot of money to erect these things. And who knows what it's going to do to the ecosystem. I mean, you're not going to be able to grow things underneath these solar panels. The wildlife there is going to disappear. So you got an eco problem with putting up all these solar things. Then you got to get the energy to where it's needed. So I'm arguing that we need something better than solar power generation. On the other hand, there's a new technology which basically says we can put a new roof on your house, or literally covers the entire surface of your roof and generates electricity at the same time. And basically, I think within 3 years, we're going to have solar roofing materials that'll be the same price as just putting a new roof on your house. And if you live in a home, about every 15 years, you got to put a new roof on it anyway. And so you might as well put one on that generates electricity, and you can go off the grid. So that's an example where you got an economic incentive, because you're not damaging an ecosystem. You already got a building there anyway. Why don't you just put a roof on it that generates electricity? And because we're living in California, I've got solar panels on the roof of my home, but it only covers 30% of the roof. It doesn't cover 100%. And moreover, it was expensive to put those solar panels on. I did it because I got a tax incentive. I did it because California charges so much for electricity. And that's what California did. They raised the price of electricity basically to incentivize us to put solar panels on our roofs. Wouldn't it be wiser to come up with a technology that makes those solar panels 5 times cheaper than what they are now? Then we don't need the government to step in and pass all these laws. But I think that's what's causing people to push back. They don't want the government pushing them around, basically dictating how we live our lives. We don't want to live like people have to live, for example, in mainland China. And so I'm basically arguing, give people a strong enough economic incentive. We don't need the government to get involved. Private enterprise is more than adequate to solve the problem. And I think the best way to solve the problem, get the government to step away from it and let free enterprise do its work.
All right, we have a question in the chat box. Chrissy's already answered the question about the shirt, but he's asking if you could explain what's on your shirt again.
It was a joke.
Okay.
These are Maxwell's equations. And if you ever took physics or engineering physics or electrical engineering, you wind up spending about 4 years studying these equations.
How
I
many
had
years?
about 4 years worth.
4 years?
Well, I mean, electromagnetic theory and thermodynamics is kind of the core of an undergraduate physics degree,
Okay.
all centered around these four equations. And when I was taught electromagnetic theory, they professors first had us work through thousands of different equations. And after we had spent years going through those equations, I said, you know what? All these equations reduced to just these four, and just made life so much simpler. But also makes the point that God designed the universe and mathematics so that it's elegant and simple and highly efficient. And incidentally, James Clerk Maxwell, who produced these equations, he was a strong Christian. He was one of the top leaders in the Presbyterian Church. And the theologians in the Presbyterian Church said he was the best of their theologians, even though he was a theoretical physicist. And I
Hmm.
can tell you, as a physics student, Isaac Newton is not the greatest physicist who ever lived, nor is it Albert Einstein. It's James Clerk Maxwell. He only lived into his 40s, but on his deathbed, he actually had all the foundations of general relativity and quantum mechanics developed. And we're talking, we're talking 1885. He had all this produced. Notice it wasn't until the 1920s that we had general relativity and quantum mechanics. People just didn't have a chance to examine his notes. That's how brilliant of a guy he was.
Okay. Thank you.
All right.
Maxwell. I
The
don't
next,
remember that now, Maxwell.
next question in the chat box is from Daniel. He said, so should we continue to use gasoline powered cars, or is there a better alternative to gasoline than electricity?
Well, right now, I would say that the most gas efficient gasoline powered cars and a few diesel cars are actually have the lowest carbon footprint. When we talk about hybrid cars, but these hybrids have to have these big batteries in them, and it's a big carbon footprint to produce those batteries, and they only last 150,000 miles. So when you take that into account, you're actually better off with a very efficient gasoline or diesel powered engine. Now, I have a friend in Canada who has a Tesla. He drives that Tesla about 300 miles a week, and he is able to do that for less than 50 cents. Why? Because where he lives, hydroelectric power is so incredibly cheap. He can drive his 5-passenger Tesla, which is able to go from 0 to 60 miles per hour in 3.9 seconds. So it's an incredibly powerful car. He can do that for 50 cents a week. I mean, how much do you pay to drive your car 300 miles a week? I'll bet you it's a lot more than 50 cents, which means if we can find a way of getting a really cheap source of electricity, electric cars are the way to go. But if your electricity is coming from a coal-fired plant or it's coming from um, you know, a natural gas power plant, you're actually better off driving a gasoline-powered engine.
What is Maxwell's first name again?
Pardon me?
What is Maxwell's first name?
Oh, James Clerk Maxwell.
James Clark.
Yeah, I mean, Maxwell not only developed all the equations in electromagnetic theory, he did that for thermodynamics as well.
Hey, Doc, are you familiar with Graham Hancock?
Graham Hancock? No, I'm not. Don't know the name.
Oh, interesting. I'd recommend you to take a peek at his work. He's an archaeologist. Well, I'm curious as to where, I guess, some of the discoveries, maybe from 20, 30,000 years ago, when the shoreline was a lot lower than it is now, they found, underwater shorelines that's covered by the water now.
Right.
When do you think How do you account for those civilizations pre? I'm guessing this is antediluvian, before the flood, right?
Yeah, well, I think the flood took place during the last ice age. The reason why is Genesis 8 tells us it took 7.5 months for the flood waters to recede.
Mm-hmm.
For it to take that long, you'd have to have a huge quantity of melting snow and ice. And therefore, I think the flood, Noah's flood, was occurring during the last ice age. And if you remember that chart I showed you, the temperature jumping up and down
Yeah.
throughout the ice age cycle, that means even during a 90,000 year ice age period, you're going to get brief episodes where the global mean temperature jumps up by about 10 degrees. And I believe Noah's flood occurred when you had one of those temperature blips, which caused a huge amount of melting snow and ice. And likewise, you got water coming up from underground aquifers, as it says in the text,
Mm-hmm.
which tells us that we're probably looking at a location for Noah that would be in the Persian Gulf rather than Mesopotamia, because there's a really big underground aquifer underneath the Persian Gulf, but not such a big one under Mesopotamia. But during the last ice age, virtually the entirety of the Persian Gulf was dry land. During the last ice age, you've got sea levels that are 300 to 400 feet lower than they are now.
During the last ice age, we have sea levels 300 to 400 feet lower than they are now.
Correct.
Mm-hmm.
And in fact, the oldest written record of a human history is not in Mesopotamia. It's in the Queen Charlotte Islands. There you had natives erecting totem poles. On the totem poles, you got carvings that are kind of like hieroglyphics, and they document a period when the Queen Charlotte Islands off of British Columbia were joined to the mainland. But what's happening is that with the rapid melt of ice from the last ice age, the sea level was coming up so rapidly that natives on the Queen Charlotte Islands were not able to return to the mainland. And so they were literally cut off from the rest of human population for 10,000 years. But their totem pole record documents all this and documents the rate at which the sea level was rising. And we know from carbon 14 dating that happened 10,500 to 11,000 years ago. So this is more evidence that people living 10,000, 15, 35,000 years ago were just as technologically capable as we were, but they didn't have the climate stability to sustain the technological development. And so this idea that writing doesn't go back very far, we now know it did. But again, small scale and local.
Yeah, he also dates the Sphinx, the pyramids and the Sphinx back to about 12,500.
Yeah, I would be skeptical of that claim.
Mhm.
I've been to the Sphinx, and you can see just how heavily eroded it is.
Water erosion.
Well, it's not just water erosion, there's chemical erosion going on as well. The Sphinx today does not look anything like it did 2,000 years ago.
Right.
And it's unlikely that it would have been in the current state that it is, if indeed it's 12,000 years old.
Mm-hmm.
I mean, it would be unrecognizable today if it was that old.
Yeah, I'd highly recommend. I'd love to hear what you thought about, one of his, I don't know what you call it, one of his documentaries.
Yeah, I mean, the one piece of advice I would give is you want to judge archaeological claims by the archaeological community. And so, for example, I'm trying to think of his name. He's at Ohio University, a Japanese American archaeologist. He's the chairman of the department there. He's retired now. But we consulted with him a couple of decades ago, and he was able to put us in link with a whole community of highly reputable archaeologists. And they communicate with one another, and they can basically tell you which archaeologists you can trust and which one you need to look at their claims with a big grain of salt. So, and Again, I've been trying to train people how to evaluate stuff you see on the web. Most of the science material you see on the World Wide Web is not at all trustworthy. And I tell people, only give credence to web articles where they cite the peer-reviewed literature and give you links to the peer-reviewed literature. And the wonderful thing about the peer-reviewed science literature today is that you have search engines like the one that NASA runs and the one that PubMed runs, where you not only get to see the paper and read it for yourself, you can read all the other papers on the same subject and see the critiques of the paper, whether the critiques are favorable or they're not favorable. And incidentally, the abstracts of every science research paper published is available to the public free of charge. So the internet is amazing in that you can read any paper you want, at least the abstract, without having to pay any money. And most science journals make the articles free to the public in their entirety after 2 years have gone by. So if it's more than 2 years old, you can read it for free. And I'll give you an inside tip. The preprint on which the peer-reviewed paper is based, preprints are available free to everybody. And so if the paper got published, you can usually go to the preprint and see the different versions. And you'll basically, if you go look at the latest version, it's going to be very close to the peer-reviewed paper, and you don't have to pay any money. So that's a way to get around the paywall.
Is it kind of difficult though, especially for people like us though, to find reliable sources since a lot of Christian science is often kind of shunned by the main non-Christian communities?
Well, there again, I would, I mean, there is that shunning going on. And I can tell you that much of that is for a very good reason, because a lot of Christian science papers that are out there are not very credible. And you say, what percentage? Over 90% is stuff I wouldn't trust. Now, there is 10%, which is a very high quality. And incidentally, you typically get high praise for those papers, even from scientists who are not believers. In fact, I can tell you, having attended scientific meetings, they really appreciate Christian scholars, mainly because we Christian research scientists have a reputation of leaving the laboratory or the telescope in better condition than when we received it. So when I was at Caltech, the non-Christian astronomers always wanted to follow me after my observing run because they knew that I would leave the telescope in better condition than I found it.
All right, looks like there's another question in the chat box. This is from Aaron. He says, I want to know if Hugh has changed his mind about UFOs at all in the light of the new stuff.
Yeah, I wrote a book on UFOs in 2002. It's called Lights in the Sky and Little Green Men. Although our publisher told us we probably could have sold a lot more copies if we said it was Lights in the Sky and Little Green Women. So that may have been a marketing mistake. But we've not changed our position. What has happened recently is that the government of the US and different Western governments, and Russia as well, has released classified material on UFOs. You know, kind of being on the inside, I was aware of that classified material, but now it's publicly available. But it's giving people the impression that there's this huge upsurge in UFO sightings. That's not what's going on. It's the release of old material that was once, quote, classified and secret, now it's being made publicly available. But as I've looked at that release material, it simply confirms what we wrote back in 2002. The UFO phenomena is real, even when you eliminate the 99% that have a natural explanation. That 1% residual basically tells you there's something real that's going on, but it's not physical. I had Carl Sagan briefly as a professor when I was at the University of Toronto, and he totally dismissed UFOs, said it's impossible, it doesn't exist, but it's because his worldview would not tolerate the possibility of non-physical reality. As a Christian, I believe in the possibility of non-physical reality. The Bible talks about angelic beings as being real but not physical. And these angelic beings have been given by God the power to come into our realm. We can't go into their realm, but they can come into our realm. And therefore, the real question is, in terms of these residual UFOs, are we dealing with the righteous angels, or are we dealing with the fallen angels? And I basically make the case in Lights in the Sky and Little Green Men, we're dealing with the fallen angels, because 100% of the close encounters with these UFOs, there are harmful effects. It's never beneficial. In fact, I can tell you the best you're going to come away with are recurring, terrifying nightmares. Say, what's the worst case scenario? People have been killed by these encounters with UFOs. And I think we basically make the claim in our book that our explanation is scientifically testable. If you close the doors to the occult, that'll be the end of your UFO encounters. If you open a whole bunch of doors of the occult, you're going to begin to experience UFO encounters. And we give a list of all the ways that you can invite these beings to come into your life. But in terms of the hard scientific evidence for UFOs, there's now 2,000 reported crash sites. These are where a UFO comes through our atmosphere, crashes into the Earth, and when it crashes into the Earth, it leaves a crater. And so you got as much as 1 or 2 feet of a crater produced, 30 to 50 feet across. And when it goes through the atmosphere, it's recorded at moving at 18 to 25,000 miles per hour. And so the fact that we see this crater with damaged vegetation and melted snow tells us something real is going on. But we also know it's not physical, because when you go to the crater site, there's no debris, there's no artifacts from the crash. There's nothing physical to recover from the UFO. And when it goes through the atmosphere at 18,000 miles per hour, no heat friction and no sonic boom. So it's real, but it's not physical. And I think the strongest proof that we're dealing with demons rather than righteous angels is that these UFOs, with a few individuals, use automatic writing to communicate a book to humans. That's the Orontia book. It's about 4,000 pages long. A third of the content of the Orontia book is denying the deity of Jesus Christ. So that gives you a strong indication of its source. But hey, if you want the whole story, get Lights in the Sky and Little Green Men. We also produced a DVD documentary called the R UFO Hypothesis, referring to the residual UFOs that don't have a natural explanation.
All right, another question from Daniel. He says, I've also heard that the batteries in electric cars are bad for the environment, their production, and from the mining of cobalt and other rare earth materials needed to make them. Is that true? If so, would it still be better, like you said, to use electric cars once the electricity we are using to power them doesn't come from fossil fuels? Or is there a way to make batteries for the cars that would not harm the environment?
Yeah, he is making a point that the batteries that they're using in these electric cars are very expensive and need to mine these rare earth elements. There's a lot of research going on right now to try to find technology where we can make the batteries for a lot less money, with a lot less damage to the environment, and without the dependence on these rare earth elements. It's not yet available in the market, but I'm reasonably optimistic that we're going to get there. And to make electric cars feasible, we have to get there, because right now there's really no way that we could be producing 100 million of these batteries per year in the US alone. And so we're getting away with it now because electric vehicles are not the dominant vehicle on the road. When they become the dominant vehicle, we have to find a cheaper and a less ecologically damaging way to produce the batteries. And it'd be great if they would last longer.
I've also heard, I have some experience with power generation in various forms, but I've heard that the majority of solar panel production is very similar in that it uses harmful chemicals and materials and has a very heavy footprint on environments in that regard to produce them. Do you agree with that?
I do agree with that, but again, I mean, there's a mineral in the mantle of the earth, perovskite, which has the potential to give us solar panels at a much cheaper cost than we have today, without these damaging effects. And that's what the material they want to use to make this roofing material. And to me, that makes a lot more sense. Instead of just covering, say, a third to half your house with panels, you cover the entire house.
Is that a Tesla product?
Well, you can do that today. You can actually buy a roof where 100% of the roof generates electricity, but it's going to cost you about 3 times as much as just putting panels on your roof. So, but there is a potential for driving the cost way down.
Question. So I like the idea of investing the GND Green New Deal economy. I want to hear your opinion about Biden's new uh, Green New Deal, specifically using I don't know how much taxpayer money to invest the Green New Deal economy, but the using available government money to invest Green New Deal is a good idea.
Well, for example, I noticed he killed the Keystone Pipeline project. That would have actually lowered the carbon footprint of the US, because without the Keystone Pipeline, we have to import, you know, oil from other countries, and moreover, we got to transport it with trucks. You have a much lower carbon footprint if you transport the oil with pipelines rather than with trucks or trains. And so I think that was a bad move in his part. Again, it was motivated to get rid of fossil fuels in its entirety. But the plan that Biden has is basically, okay, we're going to replace fossil fuels with solar power and wind power. And right now, that has undesirable consequences. Again, I already explained why wind power is not a good option. And solar is better, but it still has its limitations. It's nowhere near as cheap as the competing energy sources. And again, if you want to give people an economic incentive, you have to make it cheaper. And the problem with solar power is way more expensive than other sources of energy. And when it's more expensive, people are going to cheat. They're basically going to find a black market way to get the energy for a cheaper price. And so if you want to avoid those kinds of options, again, just realizing we humans are fundamentally selfish. And so any solution we come up with has to be less expensive than what's out there in the market already. And it's just an extra bonus if it's better for our health, better for the ecosystem, and a whole lot less money, and it winds up stabilizing the climate. And that's kind of what I put in my book, Weathering Climate Change. There are those kinds of solutions, and we're foolish not to pursue them.
Would you
Is
agree
there
also? Oh, sorry.
is solutions with a metal water bottle?
Oh, you mean what kind of water bottle should you use? So, well,
It's the solutions using a water bottle that's like non-plastic and
yeah, I mean, the problem with buying water in these plastic bottles, you wind up throwing away the plastic bottle. I know people who keep putting water in their plastic bottles. However, if you put it in a hot car, you get chemicals from the plastic that you shouldn't be putting into your body. So in that sense, having a stainless steel water container makes more sense. But I'm old enough to remember back in the 60s when people thought, you know what, no one's ever going to buy water because, I mean, you just get it straight from the tap and it's free. So we thought it was just a total joke that people would ever buy bottled water. And then we joked, yeah, maybe sometime people will be buying bottled air. Well, that may be coming. But it's like, uh, especially in certain cities. For example, water at the tap in New York is of higher quality than water you can buy that's bottled at the source. So you're better off taking it out of the tap, and you don't have to pay any money for it. So, in fact, I grew up in Vancouver, British Columbia. The water there is of such high quality that in the old days where you had to put distilled water in your batteries in your car, you could take it right out of the tap because the water was that pure. But there's a lot of cities in the world where they got water that kind of quality.
Does anybody else have any more questions? We don't have any more in the chat box.
I have one. So I want to follow up a little bit on the Ice Age model, partially to make sure I understand and see what the long-term projection is based on whether we do A or B. So kind of a battery of questions. One would be, am I right in that if we weren't to stop ourselves from continuing on our trajectory with the human impact on the climate, that we would sort of bring around a premature next ice age cycle?
Yes.
And if and to go with that, if we do stem the tide, as it were, and manage ourselves well, how long are we putting off the inevitable, I guess?
Yeah, we are just putting off the inevitable because we are heading down towards that 22.1 degrees rotation axis tilt, which is going to make things a lot colder. So it's simply a matter of time before we do enter the next ice age. But I argue in Weathering Climate Change that we could sustain climate stability probably for another 14 to 1500 years. I don't think it's realistic to sustain it for 2,000 years, but we could certainly do it for 1,000 years and maybe as much as 1,500 years. If we do nothing and just ignore the problem and continue on the path that we've been going on for the past 70 years, then within a couple of centuries, we're going to see ourselves dropping into the next ice age. And if you want to know what the signature would be, what we've seen with past ice ages, you know that the next ice age is just around the corner when you see an accumulation of snow and ice appearing first in Western Siberia and then next in Labrador. So if those two events happen, then we basically know it's game over. We're heading into the next ice age and we're not going to stop it. But right now, there is a couple of papers I've seen which claim that we may be seeing the buildup of snow and ice in Western Siberia, but it's quite clear we're seeing no evidence in Labrador. So we're not there yet. And in fact, I got a blog article that's going to be coming out in a couple of weeks based on a new study that says, yes, we've been seeing a dramatic retreat of the polar ice cap in terms of the summer polar ice cap, but we're not seeing much for the winter ice cap. And so if we begin to see the winter ice cap retreat, then I think we're in trouble. But what's been interesting is over the past 70 years, only 2 regions in the Arctic have seen a significant retreat of winter pack ice. Whereas in the case of the summer, it's been all Arctic Ocean regions. All of them have seen a significant retreat. And what's not known is, okay, maybe we can tolerate a retreat of summer ice. How much can we tolerate before things get out of control? But long before we do that, it's like there are things we can do that we know will pull more greenhouse gases out of the atmosphere. And incidentally, it's not just greenhouse gases. I think a major ignored factor is that we notice that Alaska and Canada are warming 5 times faster than the rest of the world on average. And it's not because of greenhouse gases, it's because of the deposit of black carbon soot from homes and factories in India and China. The wind systems basically take that black carbon soot and move it from India and China and dump it over Canada and Alaska. And so we could simply eliminate the production of that black carbon soot that can make an enormous difference.
Hey, Doc, what's your view of eschatology?
Well, one reason why I'm pushing for, hey, let's put off the last ice, the onset of the next ice age by 14 or 1500 years, that gives room for premillennialists. I mean, if you're premillennial in your eschatology, you've got Jesus ruling as president of the world for 1,000 years. And looks like when you read those millennial passages in the Bible, that it's an economically beneficial system, which means we're going to have extreme climate stability during the millennium, which means we're going to have to put it off for at least 1,000 years.
You don't think he can just speak that into existence?
Well,
like he did the calming the sea?
He could do that. The other thing he might do is when he returns, he basically gathers up all the Christians and gives them brooms and say, let's clean things up. So maybe the first part of the millennium will be trying to restore order to the world. Who knows? There's not a whole lot of clues given to us in the book of Isaiah or Revelation on the millennium. But yeah, I'm personally premillennial in my theology, but Ken Samples on our staff, for example, is not. He's an amillennialist. So he says, we don't need the 1,000 years, but us premillennialists, we need 1,000 years. And I would argue the Bible tells us we're to occupy until he returns. So whatever your eschatology, we should be taking good care of the planet.
Would you say that another problem that kind of faces like the legislation stuff and the advancement of actual progress in this regard is that people become so fixated on images, like in California, they're eliminating all gasoline engines versus actually focusing on lowering carbon footprint in a realistic, economical manner, like that kind of image pursuit.
No, I totally agree with that. In fact, I'm convinced that if we really want to, sustain climate stability, we have to find a way to do it without government interference. Government interference is where you're trying to force people to do things they don't want to do, and that's doomed to fail. We're sinners after all. We're going to find ways to escape these regulations. So, I mean, one of the consequences I think is going to have from this mandate that there'll be no sale of electric cars after 2035. You're going to see that auto mechanics are going to have a roaring business sustaining the old cars. And so, and maybe that's a good thing for the economy, that we drive our cars for 30 years instead of 10 years. But I think that's what's going to happen. People aren't going to buy electric cars. They're going to try to find some way to keep their old cars running on the road. Or they're going to go to Nevada and buy a car there and bring it back to California.
Well, they're just outlaw gas stations.
Well, I could see our government doing that too. But I can also see our citizens say, we're going to vote out these people. They're making us do things we don't want to do.
Yeah, we tried that. It didn't work out that well.
Well, this is California after all. I mean, what geologists say about California? California has got faults in both senses of the word.
That's a geologist dad joke.
That's a dad joke for geologists, correct?
Those are the best dad jokes. Science-y dad joke.
It's a seismic reaction. Good job.
There you go.
Does anybody else have any questions? If not, okay.
One more question. What's your experience talking to climate change deniers? Are they nice about it, or are they like just curious?
Yeah, no, the climate change deniers are a lot nicer to me than the anti-vaxxers, for example. I just can't understand why I'm being persecuted to the degree I am by the anti-vaxxers. But what I've found with the climate change deniers, show them the data and show them how reliable and indisputable it is, and all the work that's been done in the past couple of years to produce this reliable data. And that's enough to persuade them. I've yet to meet a climate change denier who's looked at the data and remains a climate change denier. What happens is they begin to say, okay, what's responsible for the climate change? And so I know a lot of people that are adamant that the global warming is natural and is not human based. And that's one reason why I've been focusing on this graph of the past 9,500 years, actually showing that there's a slight cooling until 1950, which basically proves the point that the natural cycles are cooling the planet. But what has happened, and making the point too, if you look at the ice age cycle, those cooling cycles are really dramatic. The fact that it's only gone down by 1 degree means that something must be counterbalancing it. Now, what's counterbalancing it is human activity. And again, it's hard to deny that the acceleration of human activity has been much greater in the past 70 years than has been in the previous 9,000. I mean, ever since the end of World War II, our technology has been growing exponentially. I mean, as you're probably all well aware, your computer capability goes up by about a factor of 2 every 18 months.
And solar activity is off the chart, off the board,
Well,
out of the question.
a chapter on solar activity in weathering climate change, making the point we shouldn't only be worrying about Earth weather, we should be worrying about solar weather. Because we happen to be in a period of extremely low solar flaring activity. It's never been lower in the history of the sun. However, there's still solar flares, and we're overdue for a major solar flare. And for example, there was a flare in 1859 that basically shut down our telegraph system. If that were to happen today, it would knock out the internet. More than that, it would knock out our power generators. And there was an event in 1989 where there was a solar flare, nowhere near as big as the one in 1859, but it knocked out the Quebec power grid, but only the Quebec power grid. And the reason why is the Quebec power grid was the closest power grid to the North Magnetic Pole. And that's where you get the strongest impact from a solar flare. And it resulted in a loss of almost $11 billion in power generation. And so the Quebec government spent $1 billion protecting the Quebec power grid from a future solar flare event. But I can tell you this, it's the only power grid in the world that's protected from a solar flare. And there's a report that I cite in Weathering Climate Change, making the point, if we were to get another flare like we had in 1859, and on average it happens every 100 years, so we're overdue for that kind of a flare, the cost to the US economy would be north of $2 trillion, never mind the rest of the world. Moreover, you would have tens of millions of Americans dying because it would take 2 years to restore our power grid, and we need the electric power grid to feed our population. It's simply not possible to keep 330 million Americans fed without electricity. And so for that reason alone, it'd be worthwhile investing. It would cost $10 billion to protect the US power grid, but that's a lot less money than the $2 trillion you'd have to shell out, never mind the tens of millions of people who would die as a result of a repeat of a flare like we had in 1859. And I'm basically making the point, hey, we take out insurance policies for risks that are a whole lot lower than that risk. So just realizing, yes, we've been blessed by extremely stable solar weather, but we shouldn't count on it for the indefinite future. I believe when the Lord returns, he's going to protect our power grids.
But the solar weather has nothing to do with the heating of the planet.
Well, it does, but we're talking below 0.1%, and it's cyclical. It has an 11-year cycle. And so that's one thing I point out to the people who are denying global change, is that you can't look at what's happening today and compare it to last year. You have to average out the global mean climate over a 10-year period, because that takes out the solar cycle. But the solar cycle affects the global mean temperature by at most a few tenths of a degree. It's not a major effect. And it certainly has no long-term effect. Although if you're looking at the sun over, say, 10 million years, now you get an effect. That graph I showed you, how the sun gets brighter and brighter as it gets older and older, that will continue. But now you got to wait several million years before that has a measurable effect.
All right. Does anybody else have any questions? No.
Again, I want to say thank you for helping climate change. Again, you can do everything you want. You could, do more research, but instead you're helping us debating about climate change. I want to say thank you for that. I highly respect it.
Well, thank you for that comment. And one reason I wrote the book is to try to get the politicians out of the debate. It's like, hey, we can provide people with answers that everybody likes. There's no need for the politicians to get involved.
Great. I guess everybody could just thank Dr. Ross for coming and speaking to us. You guys
All
could
right.
unmute your mics.
Great. Thanks, Doc.
Hey, welcome.
Thank you.
Thank you.
Yeah, take care. Okay.